Gibbs sampling is one of the most popular Markov Chain Monte Carlo techniques. Many machine learning systems use probabilistic inference on factor graphs to cope with noisy and imprecise data. Unfortunately, exact inference is often intractable for real problems, so approximate inference techniques like Gibbs sampling are frequently used instead. Gibbs sampling takes an unnormalized input distribution, which can be specified by a factor graph, along with a list of variable values that can be arbitrarily initialized. Gibbs sampling iteratively selects a variable and then samples the chosen variable from its conditional distribution. After a sufficient number of iterations, the variable values approach the true distribution and can be used as a sample. The scan order in Gibbs sampling determines which variable is selected in each step. Two scan orders are commonly used in practice: random scan and systematic scan. Random scan selects the variable to sample uniformly and independently in each iteration. In contrast, systematic scan selects a fixed permutation and repeatedly samples the variables in that order. Given these two options, an obvious question to ask is, which scan order is better? In our paper, we study the mixing times of the two scan orders, that is, the number of iterations each scan requires to produce an accurate sample. A folklore claim regarding the mixing times of the two scan orders is that they will differ by only constant and logarithmic factors. In other words, changing the scan order will not affect the mixing time too much. In our paper, we show that this folklore statement is not actually true. To do so, we introduce two simple models. In these models, the mixing time depends heavily on whether random scan or systematic scan is used, and the mixing time even depends on the permutation used by systematic scan. Afterwards, we introduce a method of comparing mixing times of different scan orders with conductance. Using this method, we prove a theorem bounding the relative mixing times of random and systematic scan. Under mild conditions, this theorem implies that the mixing times differ by only polynomial factors. Thanks for watching. Be sure to check out our paper and visit our poster at NIPS this year.